Good afternoon, ladies and gentlemen. I'm Peter Goddard, Director of the Institute for Advanced Study. It's my pleasure to welcome you here this afternoon to this Institute lecture. Our speaker today is Peter Goldreich. Peter is an emeritus professor in our School of Natural Sciences, having retired from our faculty last June. After the lecture, there will be a question and answer session. Peter is distinguished for his many profound contributions to astrophysics and to planetary science, providing fundamental theoretical insights for our understanding of the rotation of planets, the dynamics of planetary rings, pulsars, the spiral arms of galaxies, oscillations of the sun, and white dwarfs, an enormous range. Peter obtained his bachelor's degree and his doctorate from Cornell. From 1963 to 64, he was a postdoctoral fellow in the University of Cambridge. After 2 years as an assistant professor at UCLA, he moved to Caltech, where subsequently he became Lee A. Dubridge Professor of Astrophysics and Planetary Physics in 1981, and then an emeritus professor at Caltech from 2003. So he's one of those rare people who's a double emeritus professor, being an emeritus professor here as well. Peter has been a frequent visitor at the Institute since the 1970s, and after spending 2 years as a visiting professor here from 2002, Peter joined the faculty of our School of Natural Sciences in 2004. Peter has an enormous number of distinctions. He's a member of the National Academy of Sciences, a fellow of the American Academy of Arts and Sciences, a foreign member of the Royal Society of London. He's the recipient of the National Medal of Science and many, many other awards. This evening, Peter's title is The Evolution of Bodies Bound by Gravity. Peter.
Thank you. It's actually much more distinguished. It's much more of a distinction to retire from a place and not become an emeritus professor. There are very few people who I know who have accomplished that. Okay, so I'm going to start off with a little bit of physics while you're fresh, just a very, very little bit, and then I'll show you pictures and comment on them. So this first slide is meant to illustrate atomic structure. It shows the nuclei. Whoops! Oh, it's the wrong button already. Okay, it shows the nuclei of three atoms, neutral atoms, with neutrons and protons in them. So we have helium, lithium, and beryllium here, and it's meant to illustrate first what particles are in the nucleus, and then the electrons that orbit around it. The scale isn't very good. In fact, the electrons are about 100,000 times farther away from the nucleus than the size of the nucleus. But they're also not in little balls. They're sort of more spread out in a wavy sort of structure. The other thing that you're supposed to appreciate from this, besides the big distance between the electrons and the nuclei, is that for neutral material, there are the same number of electrons as there are protons. Now, the sizes of atoms are determined by the fact that electrons, or actually all quantum particles, don't like to be localized. They resist being localized, and the electric static force from the protons attracting the electrons can only pull them in a certain distance. And that more or less sets the size of all atoms, and the sizes of atoms don't vary all that much, and that's why atoms with a small number of nucleons in their nuclei, like hydrogen, helium, and so on, when they form condensed material like solids or liquids, form much lower density material than heavier elements, for example, like lead or gold or uranium. So this is the sort of first rule of this. The other important thing here is that when you put material together, there's still a little bit of residual electric attraction, and this binds things in ordinary matter. So ordinary matter is basically bound together electrically, at least when it's not in a gas form, when it's in a liquid or a solid form. And it resists compression because electrons are essentially antisocial. You can only put one in each quantum state. So when you squeeze on ordinary matter, the electrons get driven up to slightly higher energy states, and this produces a back pressure. And that's why we, and almost everything that's in condensed form that we know about, like this table, the floor, the chairs you sit on, are essentially incompressible. Now, if you squeeze matter hard enough, then the electrons get to higher and higher energy levels, and eventually their energies become so high that they break free from the positively charged nucleons, and they go wandering around freely. And then we say we have a degenerate electron gas. And I'm going to talk for a while about degenerate electron gases, and also about ordinary matter. And then I'm going to come to the main subject of my talk, which is matter which is supported thermally by the relative thermal motions and essentially the gas state. Okay. So here's an example of a body that's bound by gravity. That's why it's round. But it's supported against gravity just by the fact that these electrons resist being compressed into a smaller volume. And the density in this body isn't very much greater than it would be if you took the material in the body and put it at zero pressure. Pressure inside, this is Mars. The pressure inside Mars is only a little bit, is only able to compress the material inside Mars by a little bit. If we go to a somewhat bigger body, Jupiter, sometimes called a gas giant, then we enter a new regime. The pressure inside Jupiter is high enough so that the electrons at low pressure are bound to hydrogen nuclei, or to protons, become free. They move around. The interior of Jupiter is almost entirely a metal of hydrogen. It's a very good conductor, supports a big magnetic field. That magnetic, we've got to be careful here. That magnetic field is implicated in these aurora that you see at the poles, which I'm probably not going to say much about. I just put these pictures up because they're pretty. Well, and they illustrate some of my points. Now, even though Jupiter is called a gas giant, it's not throughout, most of it, it's not gas at all. It's a liquid, and it's very, very much supported by the pressure of these electrons, which resist being squeezed. And so if you took Jupiter, which is a few thousand degrees in temperature and it's inside, and you cooled it off to zero temperature, it would only shrink a little bit. So it could exist quite happily as a completely cold body. It just hasn't gotten there yet. It's still cooling off. So that's our second example. We go to the third one. Well, now we're talking about what happens when you squeeze still harder and you put material in still denser conditions. And so I'll go through it here. If we consider hydrogen, which can form a solid at zero pressure, that solid has a density which is less than 1/10 that of water. If you compress that solid so it becomes about as dense as water, then the electrons run freely, and we already have a highly electrically conducting metal. If we keep compressing this material so that its density, I should say that the electrons at this stage are moving at something like 1% the velocity of light. If we compress by another factor of 100 in the spacing between the electrons, their velocities go up to being essentially the velocity of light. In fact, the velocity, as long as the electrons are moving at less than the velocity of light, Their velocity goes as you squeeze, the average velocity goes is 1 over the distance between electrons. These are completely cold electrons. And then you make a body which has about the mass of the sun, shown here, but a radius something like that of the Earth. So this is a picture of the Earth, but this is a cartoon of a white dwarf. We don't yet have telescopes that have the resolving power which can take a good picture of a white dwarf, so I've substituted a cartoon for you. Now this sort of body has a density of about 1 million times that of water, and it can exist as a completely cold body forever. When white dwarfs are born, and we'll discuss that a little bit more later, they're born very hot, but then they cool off, and there's nothing to prevent them from staying around essentially forever as they cool more and more. So this is one of the final states that you can have for a star when it dies, and it's the final state of stars that have masses less than about 8 times the mass of our sun. But there's a maximum mass that white dwarf stars can have, which is called the Chandrasekhar mass, and it's only 1.4 times the mass of the sun. So these much bigger stars that have masses, for example, of 5, 8 times the mass of the sun, they have to get rid of, or they do get rid of all the excess mass before they become white dwarfs. And this is not something that humans probably would have figured out without seeing it happen. But we do see it happen, and we now understand more or less why it happens. Okay, now, if we squeeze even further on ordinary matter, let's say we squeeze beyond the density of a white dwarf, then the electrons become relativistic, and their energies become so high that it's advantageous, energetically advantageous, for the electrons to combine with whatever positive nuclei are around. Let's say it's we keep it simple and just have protons, combine with the protons and make neutrons. So the electrons disappear, there's no more electron degeneracy pressure, but we have neutrons, and neutrons share with electrons 2 properties. First, they, like all quantum particles, they don't like to be confined in too small space. They resist being compressed into small spaces. They give a degeneracy pressure, but because they're heavier by about 2,000 times, a factor of 2,000, than electrons, they can be compressed by about a factor of 2,000 before they become, relative to the compression in a white dwarf star, before they become relativistic. And so the neutrons can support then, and the neutrons also are fermions. They can only exist 1 per quantum state. But the neutrons then can support a star which has a mass of about that of the sun, which has a radius which is 1,000 times or so smaller than a white dwarf. And this is called a neutron star. Now, we don't know exactly what the maximum mass of a neutron star is, because unlike the case of a white dwarf, where the electrons interact very weakly, and as they're compressed, it's only the degeneracy pressure of their motions that holds the star up, provides a pressure. In the case of a neutron star, the neutrons interact through the strong force, and when they get very much compressed together, not only are they providing a pressure due to their degeneracy or to their motion, but also because they're repelling each other through the strong force. And this means that the maximum mass of a neutron star is pretty uncertain. It's probably somewhat less than, or of order 3 solar masses, but nuclear physics is not very predictive, this answer. And observationally, we know that there are quite a few neutron stars with masses of around 1.4, 1.5 solar masses, and we don't know yet accurately what the sort of maximum possible mass of a neutron star is. But these massive neutron stars have radii of about 10 kilometers, so compared to the size of Manhattan here. And the escape velocity from their surface is about 3/4 that of the speed of light. So we've now gone through the 2 or the 3 types of bodies that can exist supported against gravity by some repulsive pressure at 0 temperature. Those are ordinary materials that make up things like the planets, the white dwarfs, which are supported by the degeneracy pressure of electrons, and the neutron stars, which are supported by the degeneracy pressure of neutrons, plus some help, significant help actually, from the strong force. The only other thing that we know about that could be the final state of objects that are being supported by gravity, which are much bigger than a few solar masses and which cool off, are black holes. And they're, as far as we know, not supported by anything. It's just gravity unsupported, which produces a singularity in our space-time. So when I go through the rest of the discussion of stars, I'm going to try to tell you how most stars avoid becoming black holes. And we still don't have a very clear idea of where the cut is, or whether it's just dependent upon the mass of the individual star, or whether there's secondary characteristics that determine whether stars of large mass become black holes or not. This is a sort of frontier. It's been for a long time, a frontier of astronomy. Okay, now we come to the first object that's supported by pressure, by the thermal motions of a hot gas. In this case, basically ionized hydrogen, a little bit ionized of other elements. Well, a significant amount of helium and then a bit of other things. This is our sun. I chose this picture because it shows some very big spot groups here, but I'm not going to have much time to say anything about them. So the sun is a sort of typical star, supported by thermal pressure. Thermal pressure associated with the motion of the electrons, the protons, the nuclei of the helium atoms, which are called alpha particles. And to a very much smaller extent by the pressure associated with radiation, with the photons that are running around inside. Now, you're probably all familiar with gas pressure. Anybody who's ever blown up a balloon or a tire knows about gas pressure. The gas pressure makes the tire, for example, or the balloon hard, and what's being resisted is the elastic stress in the material which is holding the air, which is trying to make the container smaller. So this is something that's supported by gas pressure. But a star which is supported by thermal pressure, even pressure involving radiation as well as particles, is going to cool off because it radiates its energy into cold space. And so it has only a finite lifetime. And so we're now going to explore a little bit what happens during the finite lifetime and what a star is like. So I'm going to tell you a little bit now about how we understand the star. So the first question you want to ask is the sun going to come up tomorrow? Is this something to worry about? Well, if the thermal pressure in the sun could mysteriously vanish, the sun would be gone in an hour. And we've seen it for a lot longer than that, actually for almost 5 billion years. So we know that that's not something that is at least likely to happen. Then we can ask, what would happen if all of the nuclear reactions which were providing the energy powering the sun would shut off? How soon would we know it? Well, nowadays we would know it pretty quickly because we would stop observing the neutrinos that are coming out of the center of the sun pretty quickly. But as far as the heat that the sun contributes to the Earth, this would take a long time. In fact, the temperature wouldn't drop substantially. By substantially, I mean by a factor of 2 of the sun for something like a few million years. Oh, actually, a few tens of millions of years, maybe 20, 30 million years. So the sun has a sort of radiative time scale, a time scale over which it would stay warm, which is about 30 million years. Actually, the photons get out a lot faster, but they keep being replaced by the hot gas particles. So that's the second time scale. And then the heat inside the sun that keeps the sun warm, this is being supplied by nuclear reactions, mainly by the conversion of hydrogen into helium. And this has been going on for 5 billion years, and there's enough of a supply of hydrogen that's available to the sun that it can go on for about another 5 billion years. Now, inside the sun, where the hydrogen is actually fusing to form helium in the core of the sun, the temperature is something like 20 million degrees. Extremely hot. In fact, it doesn't even matter whether we use Fahrenheit or centigrade or Kelvin. For the temperature, we're only talking about factors of 2. But the sun is actually a very low power density reactor, if you want to think of it that way. The sun produces per gram or per unit volume, it has about the same density we do, which is about the density of water, produces power at a rate per unit volume or per unit mass, which is about 10,000 times less than we do just from eating. So actually the sun is a very moderate, very well-controlled producer of energy. Now our 100 watts that we get, we're sort of a 100 watt machine. Our 100 watts in our somewhat, I hope for most, less than 100 kilograms, that actually corresponds to a power density comparable to the most massive stars, the most luminous stars. So the sun, so we're really very high power density compared to most stars. Okay, now the sun is going to die as a white dwarf. I already showed you. It'll eventually die. It'll contract to something about as big as the Earth, but with essentially with probably half the mass that it has now. Okay, so that's the first object that is supported by thermal pressure. So here's an example of the magnetic cycle of the sun. Here you're not looking in visible light, but you're looking at an image taken by the SOHO spacecraft in the line of 14 times ionized iron. So we're looking at gas which is on the order of 1,000,000 degrees. And you're looking at different images of the sun, individual images of the sun that were taken over a period of 10 years. From a time when the sun was magnetically not active to when it was at its peak of activity and then going back to inactive again. And the reason I put this up is to show that even middle-aged people or stars can have moments of passion. So I think my wife is here somewhere, but I didn't check this with her. But anyway, so you see that even though the sun is a very quiet sort of middle-aged star, it's capable of quite remarkable outputs. And also associated, this is a part of the general theme of this talk, associated with this, this magnetic activity, there's also a modulation of mass loss from the sun. The sun is losing mass in a wind, which is blowing at about 400 kilometers per second past the Earth, and all the way out, carving out a big cavity that goes well beyond the orbit of Neptune in the interstellar medium. But at least currently, the mass loss from the sun in this wind is rather small. It's only losing 10 to the minus 14 of its mass per year, and it's going to only last 10 to the 10 years, and therefore may lose a part in 10,000 of its mass at this rate over its lifetime. Probably when it was younger, it lost significantly more. Okay, and here's an example of the solar wind in action. This is a comet. This is Hale-Bopp, the brightest comet to appear for quite a long time, although it was brightest when it was on the opposite side of the sun. So you couldn't see it very well. But even when it was on our side of the sun, it could be seen very, very brightly at night. And this type of image, although not as good an image, actually gave us our first real clue to the presence of the solar wind. What you're seeing here is a tail, this tannish, yellowish tail, is the tail of small dust particles that are coming off the comet. The comet is basically dirty ice, and as the ice sublimates, about a meter of ice per year at a distance of the Earth from the sun, as the ice sublimates, some of this dust comes out, and the dust moves under the influence of radiation pressure from the sun and also gravity in sort of comparable amounts. And so you get this big fat tail with different sized particles in different parts of it. And then there's also gas released, all sorts of gases, and some of the gas is carbon monoxide. And carbon monoxide becomes ionized by the sunlight, and then it emits this very blue light. And these tails, the gas tails, the ionized gas tails, in this case shown in the CO line, point straight away from the sun. And they're not subjected very much to the effects of gravity or radiation pressure. So they're indicating that there's a wind blowing out, just the way you see the wind blowing a flag or your hair, if you have long hair or any hair. And this was a clue, or the clue, that led many years ago Ludwig Biermann to propose that there was a wind coming out of the sun. Now, I looked up how much CO was coming out of Hale-Bopp when it was at 1 astronomical unit at the distance of the Earth from the sun, and it was equivalent to that produced by 5.5 billion cars. Pretty soon we'll probably have 5.5 billion cars, but still a pretty impressive number. Okay. Now, I was told never to give in a public talk an equation, because half the audience goes with the first equation, and then they keep dividing in half with every subsequent one. But I decided I would show one slide with equation, only one, because they're actually very, very useful for this. If you're equation phobic, just close your eyes. This will be over very, very quickly. One of the problems with equations is you have to tell people what all the symbols mean, but only a couple of them are important in each one of these equations. And my son, I heard my son once give a lecture, and he showed an equation. And he said to the audience, you should think of this equation like a poem. It's really a beautiful thing. It has all sorts of information, provides all sorts of insight that you can't get any other way. And I really think that's true. Mathematics is the language of science. So we're going to just go through this equation a little bit. So this first equation, this first equation relates the energy of a ball of material, of matter, a sphere of matter, of mass m, which has radius r. G is just a constant, it's a gravitational constant. It's only we can think of it as only affecting units in this way. And the energy here is written as negative, because the energy here is reference to what this material would have, the energy this material would have if it was infinitely diluted and at 0 temperature. Then when you bring it together, some energy is released. And this is then the binding energy is the negative of this energy. So this is the actual energy. It's lower than that because the material has been brought together under the influence of gravity. So this is the energy. It goes as the mass squared divided by the radius. Then there's a wonderful theorem known as the virial theorem, which tells you that the total energy can be related very simply to the thermal energy if the body is supported against gravity by the thermal motion of particles. Actually, even if it's supported by degeneracy pressure. And this is essentially the thermal energy per particle. Oh, I should say these aren't quite equations, because you see these little twiddles here. That means that they're only approximate relations. They replace more complicated ones, but they're very useful. This K, the Boltzmann constant, is again just a constant that changes the temperature into an energy unit. So this is the sort of typical temperature somewhere deep inside this body, and it's related to its mass divided by its radius, times the mass of a nucleon, a proton or a neutron. So we have these two relations. And you can see from these two relations that if your body is losing energy, for example, by radiating energy into cold space, so this E is becoming smaller. The only way the E can become smaller if the mass stays the same is for the radius to become smaller. This E is already negative. So if the radius gets smaller, this E becomes more negative. So radiation causes bodies to shrink. They lose energy, they tend to shrink. How fast they shrink is another question, but if they didn't have any nuclear energy source, and for example, we were talking about the sun, the shrinkage would occur on a time scale of 20 million years or so. But as the body shrinks, this relation tells us its temperature goes up, because if the mass stays the same and the radius gets smaller, the temperature goes up. So this is the unphysical, at least, or the not everyday experience. Normally, we experience the heat flows from hot regions to cold regions. Just imagine hugging somebody that's warmer than you are. You start to get warmer. Sitting on a radiator, you start to get warm. But normally, the donor of heat, the hotter object, gets colder, and the colder object gets warmer. Here we have a system in which the loss of energy into cold space makes the system actually warmer, makes the temperature higher. And this is very important in the evolution of stars. So when stars start out as balls of gas, very distended balls of gas, they radiate, and too cold in the middle for nuclear reactions, they radiate energy out into space, and they get hotter in their interiors. Now, two things can happen to these balls as they contract. If they don't have enough mass, and they contract, if they have less than something like 70 times the mass of Jupiter, or 7% the mass of the sun, they'll contract, but as they contract, the electrons inside them will get squeezed more and more, and eventually they'll be supported by electron degeneracy pressure, and they'll never get hot enough in the center to start nuclear reactions. These will be failed stars, and we call these brown dwarfs. And they can just sit there forever. They're very similar, except possibly in the way we think of them forming, to planets like Jupiter. They could just survive forever. And for a long time, we didn't have any examples of white dwarfs. They're faint. They're hard to distinguish from low-mass stars. And now we have lots of them. From infrared astronomy, we've detected lots of brown dwarfs. And we also know that the total mass in brown dwarfs is less than that in stars. And this is a little bit surprising, because as we go from massive stars to low-mass stars, the total mass in the low-mass stars is more than the total mass in the high-mass stars. But somewhere before we get to the massive brown dwarfs, the way these objects form arranges itself so that the amount of mass that's born into objects that become brown dwarfs is not really very significant for the total mass budget in the galaxy. Whether this is a coincidence or has some deep physical meaning, we still don't know, because we still don't know how ordinary stars form. There are various theories, but there's no real accepted answer. Okay, so that's one thing. Bodies shrink, they get hotter inside. Now, we say that a star is born if the temperature inside one of these shrinking, thermally supported bodies gets hot enough so that hydrogen can fuse into helium. And that supplies most of the nuclear energy that can be supplied by burning fuel all the way up to the most stable elements, in particular to iron. So the longest stage in the life of every star is the stage in which it burns hydrogen. And we'll see in a little while that when we look at temperatures and luminosities of stars with known distances, that most of them have a simple relation between their luminosities and temperatures. And those are set by the fact that they're all burning hydrogen. But these equations can tell us more. For example, they tell us that when hydrogen is being burned, which is at a very specific temperature, when hydrogen is being burned inside of a star, its mass is proportional, or its radius is proportional to its mass. And if the radius is proportional to the mass, then as we go to more and more massive stars, we consider more and more massive stars burning hydrogen, the volume is going to go of these stars proportional to the cube of their mass, the cube of the radius, and therefore their density is falling down, is 1 over their mass squared. So more massive stars have much lower densities. So as you go to more massive stars, the densities go down. And because the densities are lower as you go to more massive stars, the radiation can get out a lot more easily. And so even though the temperatures inside more massive stars are the same when they're burning hydrogen as inside the sun, they radiate a lot more efficiently. And in fact, their luminosity, the total amount of energy they put out into space, scales as something like the 4th power of their mass. So very massive stars are extremely bright compared to the sun. Okay, so this is a diagram showing the temperature. It's best to look at the upper axis and the left axis in this diagram. This shows the luminosity of the star in solar units. So this is 1 solar luminosity. If we go across here, this is where the sun would be, roughly, here. So the more luminous stars are up here. They go up to something like 100,000 times the luminosity of the sun. The low luminosity stars are down here. Here are the white dwarfs that are just cooling off. And up here we have the temperature. 3,000 degrees, the sun's just a bit shy of 6,000 degrees temperature. We have stars going up to much higher temperatures. And these are stars with known distances, most of them from the Hipparcos catalog, and then some that are just very nearby. And you see most of them lie along this single path here. This is called the main sequence. This is the path on which stars burn hydrogen, and also where they spend most of their lifetime. So a star is born somewhere here, and it doesn't move very much until it has exhausted most of its hydrogen. And by that time, it's already on its way to its death. The future lifetime is rather short. Okay, I was going to say more, but I think I'd better move on a bit. Okay, so now what happens when stars die? Well, when stars of mass less than about 8 solar masses die, they end up as white dwarfs, even though white dwarfs can't have masses more than about 1.4 solar masses. And the way this is accomplished is that they throw off a large amount of material in winds, very dense winds, which blow out rather slowly, at least by astronomical standards, 20 kilometers per second or so. Blow out rather slowly, And they keep blowing out until the core of the star is exposed. And that core is already essentially a very hot white dwarf with temperatures of hundreds of thousands of degrees. Now, up until 30 years ago, we couldn't study, or 40 years ago, we couldn't study these winds. But with the advent of millimeter wave technology in astronomy, we were able to study the molecules in these cold, neutral winds as they blew out. And then we were able to connect these winds with these objects, which are called planetary nebulae. So this is a very symmetric planetary nebulae. Here's the white dwarf in the middle, tiny little white dwarf. This thing is a fraction of a light year across. You can't see it, but there's still molecular material outside this object. And what's happened is that when the core of the white dwarf was exposed, it ionized. It heated up this gas, ionized it, stripped the electrons off, and this gas glowed. It actually acts like a calorimeter. It can count the number of high-energy photons that are coming out of this hot center. And in addition to the radiation coming from this hot white dwarf, there's a very fast wind that comes out as well, and it sort of blows a bit of a hole in this. And so you see basically a spherical shell, and it's edge brightened because there's more of a path through the edge than there is through the center. And so this is the fate of low-mass stars. By low mass, we mean less than about 8 solar masses. They die as planetary nebulae. The name is a misnomer. It has nothing to do with planets. Many of the planetaries have much more complicated shapes than this one, and we still don't really understand where the shapes come from. Although, again, there are plenty of theories out there. These last for something like 10,000 years. There may be 2,000 of them known in our galaxy. About one of them forms every year. So there's about one star dying in the galaxy every year. Okay. During the time that these molecular winds are flying off these, or going off these large stars, these slow winds, mass is being lost from the surface of the star at a rate which is considerably greater than the rate at which mass is being burned by nuclear burning inside the star. So the mass loss is actually dominating the evolution of the object. It's being dominated by mass loss. And both the mass loss and the rate of burning are proportional to the same thing. You can actually divide the two out, and you can see how this all can work. The expansion of these molecular envelopes is driven by radiation pressure from the star acting on dust grains. So dust grains form in these, and then the photons come and scatter off the dust grains. The dust grains are coupled to the gas by collisions, and all of the stuff pops out. So this is why we don't find that every star bigger than 1.4 solar masses becomes a black hole. Okay, now moving on to stars that are still more massive. Stars that are more massive than 8 solar masses tend to explode. They form in their centers objects or cores that can't throw off the mass in gentle winds, but in one way or another, they create an explosion. And those that are bigger than about 12 solar masses, they explode in what are called core collapse supernova. And this is the most famous one. This is the Crab Nebula, which was observed to explode in 1054 by people on Earth, and was extremely bright as seen from the Earth. Now, this is now about a few light years across. What you're seeing here are filaments of material that were part of the envelope of this star that exploded. That's all this colored stuff on the outside. And then this sort of glow in the inside. This is from relativistic electrons, which are accelerated in a sort of nebula. The ejected material from the outer envelope of the star acts like a bag, and it holds in this material. And in the middle of this, there's a neutron star, which is spinning around 30 times a second and emitting these high-energy particles, which are doing this radiation. And you can see this somewhat better in the next slide. This is now an X-ray image of the same object, showing basically the central part of it without any of the remnant gas. This is from the Chandra X-ray telescope. And you can see here a sort of circular structure, a jet. So when we think the axis of rotation of this pulsar is just about here, and this material, these wisps actually move around on timescales of months and change. So you can see movies actually of all of this moving. It's all on the web. You just ask Google and you can get all of this. Okay, so that's the way many massive stars end. They end up producing a supernova and a neutron star in the middle. But some of them undoubtedly produce black holes. We know that they're black holes in our galaxy of sort of stellar masses, bigger than the maximum mass that any neutron star can have. But we don't have a very clear understanding either of how an ordinary supernova works in detail, or where the cut between forming a neutron star and a black hole comes in, although it's generally thought that the more massive the star, the more likely it is to end up with a black hole as its remnant. The physics that goes into these supernova calculations is similar to bomb physics, but evidently much more difficult, because even though the same people worked on it for years, after they succeeded with making bombs, they still haven't solved this one. It's not the implosion that's the problem, it's the explosion. It's the problem. Okay. This is a globular cluster, which in some sense is also supported by thermal pressure. In this case, it's just the random motions of the individual stars. Whoops. There's something like 100,000 stars in here and a few light years. The ones you see best are red giant stars, these here. And this sort of object evolves by a combination of core collapse and evaporation. If I had time, I'd go back to my equations, and I'd show you that as this sort of object evolves, evolution is driven, at least in part, by the evaporation of stars. But unlike what happens when we evaporate, even on a hot day, after being in the ocean or in a lake, and we start to get cold, when a globular cluster evaporates, it shrinks and becomes hotter, just the same as a star. But in fact, it evaporates in such a way that while it loses mass, it loses very little energy. The stars that escape carry away almost no energy. And the radius of the globular cluster then shrinks proportional to the square of the mass, which is actually amazing. And so its density in the inside goes up is 1 over the 5th power of its mass. So as the mass goes down, the density goes way up. Then it even turns on things like nuclear reactions when it gets dense enough in the center. It forms binary stars, and these can provide an energy source and halt the collapse, at least temporarily. This has been a great triumph of astrophysics to work all this out, mostly 20, 30 years ago. Okay, now I'm going to talk about systems supported by rotation. This is a much shorter part. So here's a picture from Mars of the Earth and the Moon. Here's the Moon, here's the Earth. Obviously, the Sun is coming in from somewhere on the right. And this is a system in which the Moon's motion around the Earth you can think of as being supported by rotation. The Earth is pulling on the moon, but the moon is in orbit, and it doesn't fall into the Earth. And of course, we all know that the month is quite a bit longer than the day, and this turns out then to be an important feature in the evolution of this system. This system is not a body supported by rotation. There are no bodies that are completely supported by rotation. They would be unstable. Somewhere in systems that are supported by rotation, there has to be some material that's either supported by electron repulsion or by thermal pressure. In this case, the Earth is supported by this electron repulsion. So is the moon itself, but in the orbit, we have rotations against gravity. Okay, so here's a sort of example of how the Earth-Moon system evolves. The moon pulls on the Earth, and it makes the Earth somewhat egg-shaped. Here, these are the tides, two tides, one on the near side to the moon and one on the opposite side, often pictured badly in newspapers. And then the moon pulls on this near bulge, and this slows down the spin of the Earth, and it takes some of the angular momentum, which I haven't really defined, out of the Earth and puts it in the moon's orbit. And this causes the moon to move away from the Earth, to spiral out into a somewhat larger orbit. And this has been known for a very, very long time, but now we can actually measure this expansion directly. And it amounts to something like 3 centimeters increase in the orbit of the moon per year. The moon's orbit is 4 times 10 to the 10 centimeters in size, but this is still not insignificant expansion. And if extrapolated back, implies that the moon was once very close to the Earth. We also have a record of this going back a few 100 million years in the daily growth rings laid down by corals. So we know this has been going on. It's something like the current rate for a long time. Okay, so now this expansion of the moon's orbit is accompanied by dissipation of energy in the Earth, mostly in the Earth's oceans, but also in the Earth's interior. So in transferring energy from the Earth to the moon, we have an actually calculable, just from the masses of these objects and the rate at which the moon's going out, calculable energy dissipation. With satellites, we can actually measure this shape, see where the dissipation is occurring. And this dissipation amounts to something like 3 to 4 times 10 to the 12 watts of energy. By comparison, the world's power consumption these days is about 1.5 times 10 to the 13 watts, somewhat larger. So there's no point in looking for tidal energy as a global solution to energy problem. The solar energy is a better bet, but even solar energy is only about 10 to the 4 times what we use, which suggests it's not going to be that easy to collect enough of it. Okay, so this is the way the moon moves away from the Earth and dissipates energy in the Earth. But there are also tides raised on the moon by the Earth. These aren't shown here. The moon moves in an eccentric orbit, so when it's close to the Earth, it's stretched more than when it's far away from the Earth. It makes a sort of accordion-like motion. This dissipates heat in the Earth. For the moon, this isn't too serious. But for some bodies, this is a very serious amount of energy. And here's an example. This is Io, the innermost large Galilean satellite of Jupiter. It also moves on an eccentric orbit. And in the case of Io, there's so much tidal energy dissipated because it's close to Jupiter. It's about the same distance from Jupiter as the moon is from the Earth, but Jupiter's a lot bigger and more massive. So tides are much more of an influence on Io. And in the case of Io, all this volcanic activity is due to the tidal dissipation that is occurring in Io due to its motion on an eccentric orbit around Jupiter. And here the total amount of energy dissipated is more than 2 orders of magnitude greater, more than a factor of 100 greater than what's being dissipated in the Earth. So this is a really big tidal dissipation. Okay, so now we're going to talk about disks more generally. This is a disk galaxy, believe it or not. It's a spiral galaxy, seen almost edge on. It's called the sombrero for obvious reasons. The gas and the dust are all in this flattened disk-like system. But as I mentioned before, you can't have a pure disk. You always have to have something else to keep it from being unstable, and that's this. This is this big sort of halo of light. And there's also presumably dark matter in addition, which stabilizes this disk. But this disk has spiral structure in it. It's a real disk of matter. The reason you get disks like this is when you have material that loses energy easily, but mostly by radiation, but can't lose angular momentum easily, then it flattens right away if it has any rotation. It flattens right away into a disk, very quickly into a disk. I'll show you some even more impressive disks in a minute. So this is a disk galaxy. If we look at a somewhat more spectacular disk seen face-on or nearly face-on, we come to the Whirlpool galaxy, M51. And this is a tidally driven spiral galaxy. There's a galaxy with a companion out here. And you see the spiral arms. The red light here is light from hydrogen, which has been ionized by hot stars. So the places where you see the red light, there's both gas and, more important, young stars. So the star formation is confined, or at least concentrated, in these spiral arms. Now, what's happening here is that this galaxy is basically exerting a tide, or tidal distortion on this bigger galaxy, on M51. And M51 is responding by making a spiral structure. And the gravity from this spiral structure is transferring angular momentum outward. So even though we don't live long enough to be able to see this, this companion galaxy is going to gain angular momentum, and M51 is going to lose it. And also accompanying that is because the gas and stars in M51, particularly the gas, is losing angular momentum, it tends to drain into the center of the galaxy. And this is one of the ways in which gas is concentrated in the centers of galaxies and can create and also feed black holes in the centers of galaxies. Of course, these objects have much more mass than the maximum mass of a neutron star, 10 to the 12 times more. So they can only, if they evolve enough, only end up as black holes, or have some component of black holes. Okay, and this is another example. This is just a cartoon of a accretion disk of matter close to the center of where there is a black hole, showing accretion onto a black hole and jets coming out. This is just an artist's conception. But there are probably many of these things in nature. And here we think that in these gaseous accretion disks, that the main transport of angular momentum is due to magnetic fields. And I was going to try to explain how this works, but I think in view of the hour, I'm going to skip that and just go on to my last two slides. Okay, so this is what we're going to skip. Okay, so this just shows you how thin a disk can really be. These are images of, this slide was made from a series of images taken by the Cassini spacecraft, which is currently in orbit around Saturn, when the spacecraft was passing through the ring plane. So the sun is now coming up from down below. The rings are fairly opaque, and this is their shadow on Saturn. But the ring itself is essentially a line here. The ring is 100,000 kilometers in radius, but less than, in typical places anyway, less than 100 meters thick. It's extremely thin, thinner than a sheet of paper relative to the size of paper. These are a couple of satellites that are in front of the ring. And here, as this ring is like a superhighway with a bunch of ice particles orbiting around the center of Saturn. They orbit at something like 20 kilometers per second, and the inner ones orbit a little faster than the outer ones, and they brush each other at millimeters per second speed, and this causes angular momentum to flow out through the rings and material to drain in towards Saturn. So this is a very thin accretion disk. And then just to leave you with one more picture of Saturn's rings. This is Saturn's rings seen from a completely different view. This is a view taken just before the sun passed through the ring planes. Every 15 years or so, the sun passes through the ring plane. So the rings then are illuminated essentially horizontally. And what you're seeing here is a small satellite. It's called Pan, which is transferring angular momentum from this part of the ring to that part of the ring across this gap, which it keeps open. So Pan is what we call a shepherd satellite. It keeps open gaps in the ring. And then there's another gap here with another satellite, which isn't in the image. And because the sun is so nearly being seen edge-on, Pan is casting a very long shadow. So the sun is out here. Pan is casting a very long shadow on the rings. The shadow on the rings is thousands of kilometers, tens of thousands of kilometers long. Pan is only 14 kilometers in radius. So of course the sun angle is very small. Imagine how small it would have to be if for that to be the case. This was just a few weeks before ring plane crossing of the sun. Okay, and then I'll leave it up to some smart person to figure out what this is. This is obviously something that's in the sun, right? All these things that you see, these long lines here, these are density waves that are these are spiral density waves that are being excited in the rings by satellites of Saturn. So we have collisions which transfer angular momentum out, we have satellites which can transfer angular momentum out, and we also have density waves that can transfer angular momentum out. Okay, well, thank you for your patience. I hope you didn't die from the one equation that I showed you. If you have any questions.
I think we have time for just a couple of questions.
Wow.
Well, you can tell us what that line is.
Okay, you want to know what the line is? Oh, there's one.
Oh,
Yeah.
yes.
So you said that one of those pictures with the bound system of Earth and the Moon was from Mars.
Right.
Did I hear that right?
Yes.
What asset do we have on Mars that is capable of picking up the Earth and the Moon?
Oh, we have lots of assets on Mars. Some of them are sort of defunct. I think this was taken actually from a satellite that was orbiting Mars, maybe the Mars Global Surveyor satellite. But we have plenty of assets on Mars. We have rovers that drive around. We have a big presence on Mars. And we got there first.
Any other questions?
Yeah, okay, well, one of the satellites of Saturn is inclined by about 1.1 degrees to the plane of the rings. It's not an enormously big satellite, but it's inclined, and it excites bending waves in the rings. So in addition to these density waves in which the material moves horizontally, there actually are bending waves, and these are like corrugations in the rings. And this is a bending wave due to the satellite Mimas. And it's at a place where the ring particles go around 5 times for every 3 times Mimas goes around. So we say it's sort of 5 to 3 resonance. And it's actually carrying a significant amount of energy, not enough to supply our total energy needs, but enough for more than a few households. So that's a bending wave. There are other bending waves, but this one actually is paired with a density wave. The bending wave is propagating this way, and there's a density wave propagating that way, also a 5 to 3 resonance from Mimas.
Well, thank you very much, Peter, for such a beautiful talk.